Hey there, welcome to our channel. In today's video, we will delve into the world of VLSI circuit optimization and discover how discrete mathematics plays a crucial role in achieving efficient designs. Before we dive into the mathematics, let us understand what VLSI circuits are and why optimizing them is so important. VLSI stands for Very Large Scale Integration, and it involves packing thousands or even billions of electronic components onto a single chip. These circuits power our smartphones, computers, and countless other devices we use daily. The process of designing a very large-scale integrated circuit is highly complex. It can be separated into distinct steps given in the figure. Earlier steps are high level and later steps are at low level of abstraction. Now, as the complexity of VLSI circuits increases, so does the need to optimize their layout. The optimization helps improve performance, reduce power consumption, and minimize manufacturing cost. That's where the discrete mathematics comes into play. VLSI optimization techniques encompasses various stages in the design process. Mainly, we will be focusing on partitioning, floor planning, and placement of components. Let us introduce you to some fundamental concepts from discrete mathematics that are used in circuit optimization. These concepts are graph theory and algorithms that play a crucial role in achieving efficient VLSI designs. A graph theory is a branch of mathematics that deals with studying and analyzing relationship between objects. A graph consists of two components, vertices and edges. There are several types of graphs, but we will be focusing on mainly four types. The first one is unidirectional graphs. The first figure is an example of unidirectional graph. In unidirectional graphs, if two nodes A and B are connected by an edge directed along A to B, then we can move from node A to node B, but we cannot move from node B to node A. Bidirectional graphs. They are also known as undirected graphs. In bidirectional graphs, if a node A is connected to B, it implies that we can move from node A to B as well as from node B to node A. Weighted graphs. In weighted graphs, edges have weight. Weight can be positive, negative, or zero. It can refer to length, width, or area, or any physical parameter. Unweighted graphs. Edges in unweighted graphs does not have any weight, or we can say that they have unit weight. Algorithms. An algorithm is a step-by-step procedure to solve a particular problem. An algorithm is not a complete code. It is just a step-by-step logical process to solve a problem. If we follow steps that are given in the particular algorithm, then at the end of algorithm, we will have a solution of our problem. For VLSI circuit optimization, there are algorithms like Kernighan-Lin algorithm for partitioning, simulated annealing algorithm for floor planning, and Brewer's algorithm for placement planning. And now let us learn partitioning. Partitioning is the first step for VLSI physical design. Partitioning is the process of dividing a circuit into smaller modules or sub-circuits based on some criteria. Partitioning is nothing but grouping related components to improve performance and reduce complexity. So here the question arises, why we need to partition? The main goal to partition a circuit is to minimize interconnectivity while maximizing intra-partition connectivity. Here, interconnectivity means the connection between two nodes which are not in the same partition, while intra-partition connectivity means the connection between nodes of the same partition. Effective partitioning provides better design and parallel development. Kernighan-Lin algorithm and Fiducia-Mathias algorithm are the most commonly used partitioning algorithms. We will learn Kernighan-Lin partitioning algorithm in upcoming section. Let us see this figure to understand partitioning better. Here the simple circuit is given made from AND or AND NOT gates. In the figure, cut 1 and cut 2 are the cut lines which partitions the given circuit into two sections. Here we have taken two cases. For the first case, cut line is cut 1 and for the second case, cut line is cut 2. As we can see, for the first case, cut line cut 1 partitions the given circuit into two different blocks A and B, of nearly equal size, and the interconnectivity of these two blocks is of two wires. Similarly, for the case 2, cut line cut 2 gives two blocks A and B of the same size with 4 wires of interconnectivity. So for practical implementation of the given circuit, we will consider case 1 partition better, as the interconnectivity of blocks for case 1 is lower than the interconnectivity of blocks for case 2. Now we will learn Kernighan link partitioning algorithm. It is one of the most used partitioning algorithms, and it partitions the circuit using iterative approach. The KL algorithm operates on a graph representation of the circuit. In this graph representation of the circuit components are represented by nodes, and the connectivity of these circuit components is represented by edges. Let us say we have a graph G, V, E. Here, V is the set of vertices having cardinality 2n, and E is the set of edges, and each edge has non-negative edge weight. The KL algorithm partitions V into two disjoint subsets A and B with minimum cut cost, such that the number of elements in set A equals to number of elements in set B equals to n. In KL algorithm, we choose a pair of nodes based on cut cost, and where each node is from different partition, and we swap them. After swapping nodes, we fix them to avoid repeated swapping in further iterations. The fixed nodes cannot be swapped again until they become free. Here we have some terminologies for KL algorithm. The first one is cut cost or cut size. If we have unweighted or uniformly weighted graph, then cut cost is the number of edges that participate in more than one partition, and for weighted graph, cut cost is the sum of weights of the cut edges that are cut by the cut line. Second one is cost function dV. The cost function dV is defined as dV equals to the cardinality of set EBV minus cardinality of set EAV. Here EBV is the set of edges incident from node V and cut by the cut line, while EAV is the set of edges incident from node V but not cut by the cut line. High cost implies that the node should be moved, and low cost implies that the node should not be moved. The third term is the gain of swapping pair of nodes. The gain of the swapping pair A, B is defined as delta G A, B equals to cost of A plus cost of B minus 2 CAB. Here CAB term is 0 if there is no edge between node A and node B. If there is a edge between node A and node B, then it is the weight of edge. Negative gain means the cost is increased, and positive gain implies the cost is decreased. Fourth one is the maximum positive gain, and it is represented by GM. It is the sum of gains over m iterations. Maximum possible value of GM implies that the cut cost is minimized. Here m is the number of iterations to reach maximum positive gain, or in other terms, m is chosen such that GM is maximized. In KL algorithm, we start with infinite gain, assuming that our initial partition is the best possible partition, and then we do iterations until the gain becomes minimum. After all iterations, we calculate maximum positive gain GM for all values of m, and at last we choose the best possible partition by looking at the maximum value of GM for such m. Here the KL algorithm is given. You can look at this algorithm for reference, but we will understand it through example. So let us move on the example part. Here in this example, we are given a graph G with 8 nodes and the initial partition. Our task is to perform KL algorithm and partition the given graph into 2 blocks such that the maximum positive gain GM is maximized. In the given initial partition, the number of edges that are cut by the cut line are 9, so the initial cost will be 9. Now we will calculate cut cost for all the nodes. For node A, the number of edges that are cut by the cut line are 2, and the number of edges that are not cut by the cut line is 1. So the cost of A will be 2 minus 1 equals to 1. Similarly, cut cost of B is 1. For node C, the number of edges that are cut by the cut line are 3 and the number of edges that are not cut by the cut line is 1. So the cost will be 3 minus 1 equals to 2. Same way, cost of D is 1, cost of E is 1, cost of F is 2, cost of G is 1 and the cost of H is 1. Now we will choose a single pair of nodes such that the gain is maximized. There can be more than one pair also, but we will choose one of them. For example, here for pairs C, E and E, F, we have maximum gain delta G1 equals to 3 and here we have chosen the first pair. Now we will swap nodes E and C and fix them to avoid repeated swapping and go for next iteration. Again we will calculate cost for all free nodes. For this case, cost of A is minus 1, cost of B is minus 1, cost of D is 3, cost of F is 2, cost of G is minus 1 and the cost of H is minus 1. Maximum gain delta G2 comes from the pair D, F. Now we will swap nodes D and F and fix them. After doing similar calculations, and gain for the third iteration is delta G3 equals to minus 6 and for the fourth iteration gain delta G4 equals to minus 2. After fourth iteration every node is fixed, so we do not have further iterative steps. Now we will calculate maximum positive gain GM for M equals to 1, 2, 3 and 4. So G1 equals to 3, G2 equals to 8, G3 equals to 2 and G4 equals to 0. We have maximum value of Gm equals to 8 for M equals to 2. So our final answer will be partition obtained by the end of second iteration, which is this partition shown in the figure 1.3. So that is how KL algorithm works to partition a given circuit in best possible way. Now comes floor planning and chip planning. Floor planning and chip planning involves arranging the individual modules or components on a chip to optimize various objectives such as area, power, performance and signal integrity. In partitioning section, we made partitions of the given circuit to generate sub-circuits. These sub-circuits are used to form modules and these modules are used in floor planning techniques. As we have seen, partitioning techniques aims to balance the size and functionality of the partitions, ensuring efficient communication between them, while floor planning techniques use graph theory to model the layout of the circuit and optimize its physical dimensions. Placement techniques. Placement refers to the process of determining the exact position of each component or module on the chip. This process focuses on finding the best positions and orientations for components to achieve specific goals like reducing wire lengths, improving performance, and minimizing signal delay. The aim is to arrange the components in a way that makes the interconnections shorter and optimize the overall circuit's performance. Various techniques such as forced directed placement, analytical placement, and simulated annealing are used to determine the best positions for components. These methods help in finding the optimal arrangement of the components that achieve the desired objectives. That is it for now. To learn more about floor planning and placement techniques, you can visit our website or you can also mail us on dmproject34@gmail.com. Here are the references you can look out. That is it. Thank you for watching this video. See you next time.